All right, let's look at some applications of differentials. And so let's just start with an area of a circle, pi r squared, and then let's investigate dA a little more. 2 pi r dr. And what this is telling us is that we take a circle of area A, radius r, and we increase it dA estimates this increase, which would be kind of this amount here. Okay? And so I want to propose that this extra thing is pretty much just a ring, right? It's a ring around the original circle. And the area of the ring is approximated by dA. And I want to see how that makes sense from a geometry standpoint. If we take this ring and we make a slice in it, and then we unravel it, it's going to be a rectangle. You can think about it. This thickness is dr. That's how much we increased the radius, right? The radius was there, and then we increased it by that much. Well, that's dr. This distance, well, the inside is a little bit different than the outside, but they're pretty much still both 2 pi r. And if we make dr significantly small, like super small, then actually this side and this side are the same, and it's a rectangle. And look, the area of the rectangle is just 2 pi r dr, exactly what dA is, right? And so what we want to do here is we can prove then that the area, again, this symbol for AB people might be a little foreign still, but it's coming soon in the second semester. But for BC people, they've seen this integral already. That the area, of course, is the accumulation of all the individual dAs, right? That's the definition of what area is, the accumulation of all the individual areas. The accumulation of all those areas, though, is the integral of 2 pi r dr, because that's what dA is. It's the infinitely small increase in area if we increase r by a little amount. And if we integrate this using the power rule, and again, some of you already know derivative power rules, this is just the reverse power rule. Increase the power by 1, divide by the new power. Increase to r squared, divide by 2 gets rid of the 2, and all of a sudden we get pi r squared, which is exactly what we know the area formula is, right? The area is the accumulation of all of those rings. Okay, why is this useful? Okay, I'm going to give you a good application problem. Okay, so we're going to have this city, and the city can be approximated by a circle. Okay, normally, how would you find the total population? Well, the total population of a city would just be the density, the area density, right? The people per square mile times the area, right? Let's look at the units here. Population is in people. Density is typically like people per square mile times square miles, and you get people. That's all fine if the density is constant. Well, what happens if the density isn't constant? So let's go down here and say that the density function, I'm going to use the Greek letter sigma. It's typically something we would use in physics for an area density. The density is some function of r. And let's say the density is 24 minus 3r. Okay? This would imply that the density at the center of your city, when r is 0, is 24. And the density 8 miles away is 0. Right? If you plug in 0 for r, you get 24. And if you plug in 8 for r, you get 0. Which means that the population is super dense in the center of the city, and as you get further and further and further and further away, you get smaller and smaller density. I mean, when an r is greater than that, will be a negative density. So let's only define this density 0 to 8. Past 8 doesn't really make any sense. Okay, so that's kind of like the domain restriction of our city. There's nothing outside of that. Okay, so now we could never take the density times the area because the density is changing. So how would you find the total people here? Well, you have to break it up. And you have to break it up into rings in this case. So you break up it into rings. That's maybe not the best description, but we want an infinite number of these little rings. And then the total population is the summation, right? The integral of the density, and the density is 24 minus 3r. That's the density of each ring times the area of each ring. But the area of each ring is dA, which is 2 pi r dr. And we would integrate, in this particular case, from 0, and we're going to let r go all the way to 8. Okay, so we're going to take density times area. We're still doing exactly what we did in Algebra 1, except we're going to use calculus. And the reason we have to use calculus is because we have a non-constant density, right? When in this case we have a linear, it's actually decaying. The density function, if you look at the density as a function of r, it would look something like this, right? It's getting less and less. So the resources of the city are all centralized, and as you move further away from the center, you get less and less people. This would be the only way to do it. And again, you're looking at differentials. We're making this dr super small, and we're accumulating all of those really, really small rings, each with their own individual density, right? The density when r is 1 is different than the r is 1.1. The difference at 2 and 3 and 4, they're all different. And again, we're using differentials to accomplish this. Okay? In a physics class, we might even do something more complicated than that. We might take this in a three-dimensional state. So let's say we have this sphere, and it's got a non-uniform charge density. So we would call that maybe like a rho. It's another Greek letter you'll become familiar with. Let's say it's 1 plus r. Okay, and so charge density would be like coulombs. That's how we measure charge per, let's say, cubic meter. Okay? And a coulomb, one electron, just for fun, one electron is 1.6 times 10 to the negative 19th coulombs. Again, that doesn't matter in this case, and it's negative. It just happens to be negative because electrons are negative. But just to give you an idea what we're doing here. Okay, so the same thing would apply. We can't just take the charge density times the volume. Normally, again, back in the day, to find the total charge on this object, we could just take the density times the volume. We can't do that. This is algebra. Now we need calculus. In calculus, the total charge, we would have to accumulate the density. Well, the density is just 1 plus r. In this particular case, we're getting more and more electrons per cubic meter as we move further and further away. So like the surface of this thing is jam-packed full of electrons, and it gets less dense as you get to the center. And at the center, when r is 0, the density is 1. So it's like 1 coulomb per cubic meter. So we'd have to take the density times each individual, and in this case, they're not rings, they're shells. And that's harder to draw for me, but like, there's the center sphere, and then here is the next shell just bigger than it, and then we're going to put another shell over that, and we're increasing the volume every time by this dV as the shells get bigger and bigger and bigger. But if we accumulate the volume of each shell, and again, think about each shell, the volume of a cube is 4/3 pi r cubed. But if we look at dV, that's 4 pi r squared dr. And look at this. This is the surface area right here times the thickness. But if you take surface area of something, right, the area of the surface, think of the area of the surface times the thickness, you're going to get the volume of that shell. Again, not the sphere, just the shell. It's got this little bitty thickness here that's equal to dr, and if you take dr times the surface area, you get the volume. So each one of the shells has its own volume, 4 pi r squared dr. So then this is the volume of the shell times the density of the shell, would then give you the charge on each shell, and then you would, this is like a summing function, that's the summation of 0, and you go all the way out to whatever the big radius of that would be. And again, this is another application of differentials. And again, I just wanted to show the connection of both in a two-dimensional sense. Hopefully you can see the area is pi r squared, and dA is the circumference, 2 pi r times dr, right? Looks like the derivative, but it's the differential. And then in 3D, looking at maybe a sphere, we get 4/3 pi r cubed for a volume, and then dv is 4 pi r squared dr. Again, surface area times thickness gives you this increase in volume. Circumference times some increase in radius gives you the increase in area. And again, all of these have different applications, whether it's population density or electricity and magnetism. You're going to end up using differentials. Differentials are always kind of behind the scenes when you eventually do integrals. So hopefully this gives you a little preview of things and time to go.